your Levenshtein?
Okay, that is somewhat slightly different from all the other talks, but it does relate to discrete geometry, as Oleg Musin mentioned in his talk, so nicely describing the best packing of spherical caps problem, as well as minimizing the sum of the distances, which is a discrete problem mentioned, introduced by Levenshtein. And I will talk about what a spherical code is. That is just finite subset of the sphere. The distance squared is really x minus y squared. That is 2 minus twice the inner product. And since we are going to work with the inner product, and primarily with orthogonal polynomials in -1, 1, this is the choice of describing what an energy of a configuration is. The interaction potential, that'll be just a function which is absolutely monotone, meaning that all of its derivatives are going to be non-negative on the -1, 1 interval. And some of the potentials, risk S potential, that is 2 minus 2t to negative s over 2, which is really the distance to a negative s power. And then, like I said, the Levenshtein problem would be when s is actually -1. So we are trying to form, we form the energy first. H energy is just the H of the inner product, of all possible inner products within the code. These are distinct inner products. And then the Levenshtein problem would be to maximize the sum of all possible distances on the sphere. The best packing, as S approaches infinity, only the closest one will actually matter. That is why we are maximizing the minimum distance, and this is the so-called Thomas problem that Oleg talked in his presentation about. So we're interested in minimizing energy, and we want to find lower bounds for this quantity. So more or less, distributing well points on the sphere or finding nice codes is related to minimizing that energy. Okay, I will introduce briefly the apparatus and move to the 600 cell is the important part at the end of the talk. So the spherical harmonics are just homogeneous harmonic polynomials in m variables of degree k, restricted to the sphere, and R sub k denotes the dimension of all these polynomials. And a basis will be ykj. J is from 1 to rk. And the big connection here is really the Gegenbauer polynomials, which are orthogonal polynomials with this weight. There are also Jacobi polynomials with n minus 3 over 2, n minus 3 over 2 parameter. They're normalized. We will use normalization that the value at 1 is 1. Okay? So the big connection, like I said, is that addition formula that when we sum up the kernel, which is the basis computed at x, the basis computed at y, that product, sum over all possible j from 1 to rk, this really is the Gegenbauer polynomial of kth degree of the inner product. Okay? And this gives us some error on a lower bound on the energy as follows. So the moment of a spherical code, kth moment, is really the sum of the Gegenbauer polynomial of degree k at the inner products x, y, where x and y run over the code. This can be represented that way, and a configuration is called a spherical tau design if the integral over a polynomial is on the sphere is equal to the average over that polynomial evaluated at the points of the code. Okay? And whenever mk is 0 for k between 1 to tau, then C is called spherical tau design, and this is pretty much the definition for all polynomials in that pi tau part. So the moments are positive, and really, I think I've already discussed that. And then here's how the HUN bound, error bound actually down here, can be derived, Dosart-HUN method. So the risk potential can be the underlying potential. We want something that is potentials, good potentials for lower bounds that are below that H potential. So then the energy over, if we have H here, will just be greater or equal to the energy over whatever that F is. And F will be, in general, a series, but really that'll be, in most cases, a polynomial. So from a certain point on, all of these will be zero, all of these Fk coefficients. So this is how we derive the energy of the code. Here we drop all of these guys because they were non-negative, except for the first one, and then we get that Dosart-HUN bound. And indeed, we want to maximize this quantity over these polynomials or these series. That's what the linear programming method really consists of. Okay? So F is one important condition is up here. F of t is less or equal to H of t. H of t is the underlying potential, whose energy we're trying to find bound up. We want the coefficients, the Gegenbauer coefficients, to be non-negative. And then really everything becomes, this is the Kisin, the Kisin potential, but I'll skip that part and focus on maximizing that quantity subject to this class. This class, A and H, was really the good potentials, F less or equal to H, all right, with a non-negative Gegenbauer coefficient. So we want to maximize that quantity, and if we denote that with W, that supremum, over some subspace, we will usually consider the full polynomial space up to a certain degree. But as the lifting of the framework shows, we actually will consider also subspaces. So that's important for the kind of discussion later on. And really, the whole scheme works because of the quadrature rule. So let me explain a little bit about the quadrature rule. So 1nth quadrature rule is exact for polynomials or functions in that subspace if the integral, this is gamma n, is normalizing constant, is equal to f of 1 over n plus summation rho I f alpha I, and alpha I are nodes and rho I are weights, and they are non-negative weights. That's what we are asking for. And if we have a spherical design, then with the inner products, we really can use them as the nodes, and rho i's are just simply the densities of each inner product, how many times it's met within the possible distances. All right? So moving on, just one example with the simplex. The regular simplex actually minimizes a whole bunch of energies. And if H is some convex increasing function, really what we do, then all of the inner products are just a minus 1 over n. And all we have to do is interpolate right here. That's a good potential. All right? And when we compute, it has non-negative Gegenbauer coefficients down here. It's easy to see. And therefore, it will be a lower bound according to the Dosart-HUN method. But at the same time, it's attaining that energy is attained for the simplex is equal to that lower bound, therefore it's the optimal one. When we have the 2n, the cross polytope, it can be done in the same way. The inner products that exist there are -1 and 0. Okay, so passing a parabola that interpolates at -1 and touches the potential at 0 is actually, these are the Gegenbauer coefficients, and whenever we consider these kinds of potentials that all of the derivatives are non-negative, then indeed we can verify that this is a good potential and it will minimize. In the same manner, the icosahedron was shown for various potentials. The Corkin-Zolotaryov lattice, the Leach lattice, etc., has been shown to be optimal. Now, universal lower bound space, this is, in general, when we consider it, this is really the expression in the Dosart-Yudin bound. And we are trying to maximize this quantity over all polynomials f that are good. And really, we are maximizing this quantity. But if f is less or equal to h, and these rows are positive or non-negative, then that inequality is straightforward. All right? So this is a bound on that linear program that we are solving. If this bound is attained, we call that ULB space. And if there is only one h, only one interpolant f that satisfies these interpolation conditions and stays below, etc., then that's called tight ULB space. The Hermite interpolation that is necessary because f has to stay underneath h, it will not only interpolate at a certain point, but it has to also interpolate the derivative. Okay, so there is that necessary match whenever the mode is internal. Okay, so sharp codes. Here, the seminal paper by Kumar established universal optimality of a whole bunch of codes, and they were sharp codes, namely codes that have m inner products and that are 2m-1 designs. For such inner products, we can actually derive this, and alpha I will be these inner products. So this actually works. They have shown that all sharp codes are universally optimal, meaning that they minimize the energy with that many points, or cardinality that many. And further down the line, the Levenshtein framework actually tells us that 1n quadrature exists if n is bigger than some number, that is the Dosart-Giotto-Seidel bound. And this is a result that was published in Constructive Approximation last year, the so-called universal lower bound. This is by the collection of authors in this talk. So our lower bound was really this quantity, and it is possible these alpha I do not depend on the potential. That is why it's universal. All right? But the thing is that sometimes this can be improved. One of the exceptions, and the only exception to the universally optimal codes, was the 600 cell. 600 cell has 8 inner products, but is only 11 design, not 15 design. Had it been a 15 design, we would be able to prove it with the sharp code approach. However, it is almost 19 design. Only the 12th moment is positive. Okay? So whenever we consider lambda, such a subspace, that makes that 12th coefficient, Gegenbauer coefficient, 0, that'll be okay as long as we find the right subpotential of polynomial. So this is something I want to draw your attention to. And moving on, these are important in the analysis are the so-called test functions introduced by Boyvolenko, Dragnev, and Bumova in '96. These are really the quadrature rule for the Gegenbauer polynomials. All right? So whenever we have a subspace, okay, such that all of these test functions are non-negative, then we have a match of the maximum, that was the supremum. So the linear program on the smaller subspace has the same solution as the linear program on the larger subspace. So the only improvement that is possible is when there is actually a negative test function. And now I'll move to the examples. So this is the 24 cell, okay? And in the 24 cell, it's also the solution of the Kisin number problem. It's conjectured to be a maximal code, but that has not been proved yet. It's not universally optimal. This was shown by Conway and Elkis-Kumar. And here is the Levenshtein framework. So we have 3 nodes, okay, and weights. And when we test the test functions, the 8th and the 9th are negative. Now, almost always, not almost always, in all of the examples that we have considered, the first 2 test functions here with the polynomials of degree 5, the Levenshtein polynomial is really a polynomial of degree 5. So the test functions that we're interested are 6 and 7. They're positive, they always will be. And 8 and 9 are negative, so that is why the lambda that we consider is skip 2 at 2. So we skip the 6th and the 7th Gegenbauer polynomials, and we add the 8th and the 9th. All right? And in that subspace, we're able to determine a quadrature. These are the nodes, these are the weights, and it ends up then that all the other test functions are positive. So this is really that series that I wrote. The optimal guy is a combination of these polynomials. All right? And the rest of Babenko arrived at these nodes just from the context of maximal codes. So maximizing the minimal distance. All right? The 600 cell is the next step. For that, we want to somehow factor out the potential, because we are considering any kinds of potentials, and we are really interpolating at these, at some nodes which come from the quadrature. We interpolate the potential, so our bound does depend on the potential. However, to verify the conditions, all we need to do is to look at special polynomials, and they are the interpolants in the new subspace of the partial products. I'll explain what partial products are in a bit. Okay? So, because the divided differences can be written down as a corresponding derivative, these coefficients are non-negative, and whenever these guys are actually with positive Gegenbauer polynomials, we will have positive Gegenbauer polynomials for F. All right? Expansion, I mean. And this is the 600 cell. I'll just show you so this is the first step when we move from 6 nodes in the Levenshtein framework, okay, degree 11. We move to degree 15 with skip P12 and P13, getting 7 nodes, and correspondingly, this is actually a 4-term combination of the Gegenbauer polynomials. These new test functions are positive, so this solves the LP in P15. How about The next step. Well, the next step is degree 17, and Khan and Kumar, they considered a polynomial, you know, that's how they proved the universal optimality. They considered a polynomial of degree 17 that had the 11th, 12th, and 13th Gegenbauer coefficient 0. Actually, we proved that all of the optimal polynomials of degree 17 belong to this triangle. So how are the other 2 points of the triangle determined? If we have the 13th and the 12th and the 13th coefficients 0, and the 11th, we want interpolation at -1. That is this polynomial. Then 11 and 12, 0. Interpolation at -1 of the derivative is this guy. And then all convex combinations are the polynomials of degree 17 that do solve. And the proof for these guys that they are with positive Gegenbauer coefficients and staying underneath is really very simple.
Thank you.